This is Lab 2, Motion of a Falling Object. The objective of this lab was to record an object falling from rest. I was then tasked with creating two computational models of this motion, including the effect of gravity and the effect of drag on the system, which in my case was the baseball. The observations made during the experiment would then be used to confirm Newton's second law, also known as the momentum principle, which states that the acceleration of an object is dependent upon the net force acting on the object and its mass. In this experiment, I will observe a falling object that will speed up over time. This can be shown in the formula below, F equals ma, in which the force varies directly with the acceleration. Because of this, we also know that the acceleration will be equal to the force of gravity, and without taking into account the drag force, I will be calculating the weight force. The second force, whose magnitude will be in the opposite direction of the object's motion, will be the drag force, and this is the result of the product of the proportionality constant b in the formula and the magnitude of the speed squared. Prior to this lab, I predicted that the observed motion would be best modeled by the computational model that includes both gravity and the drag force, because it would be more accurate by considering all the forces that could have potentially interacted with my object. For my lab, I dropped a baseball falling in a straight line moving along the negative y direction and tracked its motion in Tracker. To the right, you can see that the system in this experiment is the baseball I dropped, and the surroundings was the earth and potentially air if you're considering a drag force. Due to these forces, the baseball is dropped at an increasing acceleration moving along the negative y-axis. After uploading everything to Tracker, I analyzed this data and set the initial conditions of the experiment, including the system's mass and length based on the diameter and mass of a standard baseball, and I included the observation start and end time, which spanned 0.588 seconds overall. Additionally, I set the initial position and velocity to 0 meters and 0 meters per second, respectively, because I started analyzing the baseball's motion at the first frame, and the ball started at rest initially. To the right, you can see how I track the ball's motion in Tracker, and below that is an enlarged graph from Tracker that shows the ball's y-component position with its corresponding time. It is important to notice that the position is not changing at a constant rate, and the slope gets steeper as time progresses, which means that the net force is non-zero. And in this case, it also indicates that the velocity is not constant, which makes sense because the ball is speeding up as it continues to fall. Here we can see how I created my two computational models that should help predict the motion of a falling object. For both models, I used the same initial conditions shown below, but the important thing to realize here is that I defined the Earth's gravity to be 9.8 newtons per kilogram, and I defined the direction the object will move along using the variable j hat. On this slide, you can see the GlowScript code I wrote to include only the gravitational force acting on the object. I did this by first calculating the weight force shown here, in which I multiplied the mass by the gravity and negative j hat since this force points downward. Because this is the only force considered, this is the net force, and we can then proceed to use the momentum principle shown here, in which we update the velocity and use this new calculated velocity to update the position and advance the time by 0.001 seconds iteratively until I reach my end observation time. After doing this, it produces the graph shown to the right. Notice how this graph produces a similar graph to Tracker's and shows a similar trend demonstrating that the net force is non-zero and the ball speed increases. Also, you can see a snapshot of an animation that shows the falling ball and the gravitational force acting on it, which is pointing downward. Next, I created my second model that includes both gravity and the drag force. I started this the same way by calculating the weight force and finding a proportionality constant that fit my data. After doing this, I calculated the weight force and calculated the drag force, whose magnitude is proportional to the square of the ball's speed, but pointing in the opposite direction of the ball's motion. Lastly, I applied the momentum principle once again in the same manner. To the right of this graph, we can also see another snapshot of this model's animation and realize that the drag force opposes the gravitational force, since it's in the opposite direction, and the drag force's magnitude is smaller than that of gravity because gravity is more dominant in this experiment. But the drag force does decrease the gravity's effect compared to the first model. After placing all graph data on the same graph, we can see that both models are very accurate to my observations highlighted in blue, but the drag force appears to be more accurate, which makes sense considering that I fit my second model to my observations using the proportionality constant. But it is possible for this model to be more accurate if I use a better value of b. Overall, these models and my observations prove that Newton's second law is at work and is very useful for predicting the motion of falling objects as well. Thinking about this lab, I don't think that either models predict the terminal velocity because neither one seems to appear constant after some time, but this is possibly due to the extremely short time of this lab. But if this time was longer, I think the model including the drag force would predict a terminal velocity. Lastly, if I were to throw the ball down instead of dropping it, I believe the terminal velocity would eventually settle down to the same terminal velocity as if it were dropped, given some time, because all that would change is the added downward force and the initial velocity. Thank you.